Okay, so now let's take a look at what happens with volume of cross sections. We'll see what we got. First of all, what we do is we've got some kind of a solid, and we have some kind of a region here. So let's go ahead and graph that region. So we don't have to be too particular. So 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4. Should have some markings down, of course, what they are. So this first line, negative 2x, sorry, 2x minus 4 is this line here. The line 8x minus 2, or sorry, 8 minus 2x. So y-intercepts 8, slopes negative 2. And we get that line, x equals 0, is this region right here. So in that triangular region there. So might be a good idea to get in the habit of labeling what they are. And then, so now what we have here is cross sections perpendicular to the x-axis are semicircles. So perpendicular to the x-axis, so like right there, that's a semicircle coming out and up above it. There's another one here and another one here, and so on and so forth all the way across. Well, what does that look like? Well, let's take a look at that. So here are those two lines, and we have just that triangular region, and that's what we see there. But we see these vertical lines going in here. It's hard to see sometimes because there's a lot of them. A whole bunch of semicircles. By the way, those are just things to make it look like it. So we're looking down on top of the XY plane, like that's the floor. So our regular coordinate plane here is the floor. So that's what we're looking at. So let's turn our view. Now we're looking along the floor. So this is the XY planes down here. Now we're looking at the vertical. We could see how these things come up. Now that still may not look like, what do you mean by a semicircle? Well, let's turn and look at it from looking at through the origin. So we're looking at that stuff from this side here. So still along the floor, but looking at it straight along that side there. So now you can see the semicircles along, around, and around, and around, and around like that. If we look at it from the other side, looking down from the positive side of the x-axis, so looking from this side this way, still the semicircles. So that's what we're doing. So let's go back to here. Well, how do we find the area of a semicircle? Well, that's half the area of a circle. So this here, that value actually is going to be the diameter. So how do we get the diameter again? Just like we did for the area, top minus bottom. So 8 minus 2x minus 2x minus 4. So the diameter is 8 minus a negative 4, negative 2x minus 2x. The radius is half of that. Or 6 minus 2x. Okay. So now the area of one of those semicircles, one of these semicircles, is 1/2 pi times 6 minus 2x, quantity squared. Now, that's area. when they have a little itty bitty thickness, a delta x, we have a little bitty thickness, little bitty volume. Picture if this, instead of being just some solid that you don't know what it was made by or whatever, was stacking up a whole bunch of pieces of paper like that. The paper itself has a very small thickness, but when you get a whole bunch of them up together, they actually look like a volume. You actually see the volume there. Now, of course, what do we do with those? Add those up. From what x value? From what semicircle? It's the semicircle to the very, at what x? 0 to what x? And I did the algebra before, setting the two equal. You get 3. That's it. So pi over 2 times 1/3, 6 minus 2x cubed times the negative 1/2 from 0 to 3. That negative 1/2 comes from doing a substitution. I did a substitution in my head because if I take 6 minus 2x as the u, dx is actually then going to be negative 1/2 du. And that's what I've seen. We've seen that enough. We've seen that a lot. So can you do that? Absolutely. And now could multiply those factors in front. So negative pi over half times 3 times, so half times 1/3 times 1/2, so it's a 1/12. 6 minus 2x cubed from 0 to 3. Now don't worry about the negative. Sometimes these negatives all work out nicely for us. It happens. So that's 0 cubed is boring. Minus 6 cubed is 216. But wait, that's a negative 216. Ah, you're right, but notice the negative out here. So that volume is 18 pi. So now, how are we going to think about this to do these in general? Well, anytime we look at stuff with cross sections, our first thing is, what's the area of the cross section? We need to find out what the area of a single cross section is. In this case being a semicircle, we're going to fill in the forms for that formula. Okay? And then 2, of course, we've got to know the region and the bounds, from where to where. Many times that region is going to tell us what it is, or it'll give in the description. And then the third one, of course, is you set up the definite integral. And that gets you the area, or the total volume. Because again, finding one little itty bitty area, the dx, the d or dy could be, going to turn it around into a small volume, find out where we're adding them up to, and then actually doing it. So let's look at the second one. Now this one I'm not going to go ahead and, what do we do with, I'm not going to go back and forth on how do we create that perspective we saw in the other one without actually doing it. Well, like everything, well, we can add perspective in a drawing by tilting one of the planes. I'll move that over just a little bit. So the y is on a slight tilt. So 1, 2, 3, 4. So our x is not going to go truly vertical. We're going to do it sideways like this. Now, is this imperative? No. So let's go ahead and look at these graphs. Now, recognition of those graphs should be good. We should be able to recognize that this is going to be a semicircle, because if we go ahead and solve for, get rid of the square root, we get y squared, and then turn around plus x squared. But this first one here is the top part of a semicircle, radius 3. When I say top, the positive part of the semicircle. And this one, of course, would be the negative semicircle centered at the origin with a radius of 3. If you prefer to think about it and actually see y squared okay to recognize that circle, go right ahead. So now, perpendicular, so there's the region. Now what kind of cross sections we have? Cross sections are squares, and they're perpendicular to the x-axis. So here's the x-axis perpendicular, so that there is one side of the square. I know it doesn't quite look like the square, that's issues with perspective and drawing it. Practice we will. So now, perpendicular to the x-axis means we're adding them in dx direction. All of these rectangle or squares that are going this way are going stacked up in dx direction. If it was perpendicular to y, they'd be shaped differently, so it would go in dy. Anyways, so area of a circle, area of the square, the cross section is side squared. So what's the length of that side? Well, high minus low, top minus bottom, big minus small. So side is square root, the positive square root minus the negative square root. I've got two of them. So now for the area of the square, you take that 2 square roots 9 minus x squared squared. So that's the value, that's the area of one little slice times a dx. Now creates a itty bitty little volume from -3 to 3, from the region, from what x to what x. So 4 times 9 minus x squared. You can distribute if you want. I like factoring out the 4 and then integrating or finding the antiderivative. Less multiplications inside A. So 9x minus 1/3 x cubed from -3 to 3. By the way, if you see something about the region, a relationship with the region, go ahead and use it. If not, don't. Well, and then just go ahead and do what we normally do. So evaluate at 3, evaluate at -3. Multiply all that. That's going to be there, multiply all that by 4, and you end up with 144. And the units would be, if we're thinking of units, there wasn't any given, so we're not worried about them. It would actually be units. It'd be nice if I could spell cubed. So again, area of the cross section, I'm going to add them up from where to where. And then that's my definite integral. So the whole thing, when you see the cross section, is what's the formula for the area of that. So try the other ones. Again, different areas, different things. You may have to look back at some of those area formulas. All right? Go get it.